And now next speaker is Ji Yan Ham.
So today I'm going to talk about an explicit formula for the A polynomial of the knot with Conway notation C2 and 4. We'll skip to next. In 1994, Cooper, Color, Gillette, Long, and Shallon introduced the A polynomial ALM of a compact three-manifold N with a single torus boundary. Its variables are eigenvalues of the meridian and the longitude under the representation from pi1 n into SL to C. One of their main results is boundary slopes are boundary slopes. That is, the boundary slope of the Newton polygon of ALM is the boundary slope of an incompressible surface in N. A polynomials are related to volumes, Chern-Simons, cusp shapes, Alexander polynomials, AJ conjectures, etc. In general, explicit formulae for A polynomials are difficult to compute. By one computation, A polynomials are known up to 8 crossings and at most 9 crossings and many 10 crossings. Recursive formulas for A polynomials were known for twist knots by Hoste-Shannon, a family of pretzel knots by Tamra and Yokoda, and by Garofalidis and Medman, and some double twist knots by Peterson, cable knots, and by and iterated torus knots by Li and Zhang. These are recursive formulas, and for explicit formulas for A polynomials were known for two-bridge torus knots by CCGLS, Cooper, Color, Gillette, Long, and Shallon, and by Fumikazu, twist knots by Matthews and Mihen Lee. We did almost the same thing. Knots with Conway notation C2 and 3 by Hem and Lee. Twists whited links by Tran. Recently, Hugh, Matthews, Purcell, and Thompson gave formulas to compute the A polynomials of some manifolds obtained by Dan Billings. They say they are somehow Ptolemy identities. Here we present an explicit formula for the formula for the A polynomial of the knot with Conway notation C2 and 4 up to repeated factors. This is the main purpose of this talk. The main purpose of this talk is to introduce the explicit formula for the A polynomial of the knot with Conway notation C2 and 4 up to repeated factors. Now, here is regular two-dimensional projection of C2 and 4. This is for n greater than 0, and the right side, this is for n less than 0. You see the 4 crossings on the top and 2 n crossings on the bottom. One is for positive, one is for negative. Okay. Jakob, can I turn up your mic? Is it okay to turn up?
Okay.
Okay, thank you. I cannot do that. I cannot do that. So maybe I don't have any permission. Anyway, now the fundamental group of C2 and 4. This is the fundamental group for the knot. We saw this before, this knot. There are two generators here, S, T, same here, S, T, and the relations you just read from the graph, and you have S, W, T inverse, W inverse is equal to 1. Here, W is TS inverse, TS inverse twice, T inverse S twice to the n. And the slope, you can see the slope from the graph. These are 2n plus 1 over 4. And you read up to mod 8n plus 1, then you get this one. Now, representation of xn, x2n. What is the x2n? Let us denote the exterior of C2 and 4 by x2n. Then, given a set of generators, ST of the fundamental group pi1 x2n, let S is the image of small s, T be the image of small t, and the entries are M1, 0, M inverse, M0, 2 minus M squared minus M to the minus 2 minus X, and M to the minus 1. And C here is somehow the matrix having the trace 0. Well, then the Riley-Mednick polynomial of C2 and 4 is the defining relation for what? Let R be the harm pi1 x2n to the SL to C. This is the representation variety. The defining relation of pi1 x2n gives the defining equation of R pi1 x2n. So we have the defining equation of pi1 x2n. We read this from the graph. And then using the relation in the matrix in SL to C, you get the polynomial Pn. And the defining equation turns out trace SWC. We have S here, T here, C here. That's why we call this Riley-Mednick polynomial. You could just use large S, large W, which is matrix, large T inverse, large W inverse is equal to 1. But then trace SWC for me is a little bit easier. So that's why I'm using the name. Originally, the polynomial is known for Riley, but then the trace SWC is known for discovered by Mednick. So I call it Riley-Mednick polynomial. Then the polynomial is like this. P2n, you just compute, and then you get this one. This is the recursive relation that I got from former paper with some initial conditions here. Initial conditions P minus 2, some P0, and I used the two initial conditions for P0 for n negative and n positive for convenience of computation. And then I use the same P because there is no confusion. And P2 and Q. You see the recursive relation has QP, something like this. And then you solve the recursive relation, you have the explicit formula here. So you have explicit formula here. Now, this is the defining relation of the representation variety. You can get somehow the relation. This is relation we get from the, again, formal paper. And from here, now L, you see that I wrote this as a function of x and m, but actually L is a variable. So here you have x squared here. You solve for x, then you have radical. You get radical here. Now you are almost done. Let us denote the A polynomial of knot with Conway notation C2 and 4 by A to N. The following theorem gives the explicit formula for the A polynomial of C2 and 4. Now, we had explicit formula of P2 and X, and then you plug, substitute the solution we get here. For X, you have P2 and G here, but then you substitute U here. For G, you get the genuine polynomial. The genuine polynomial is A to N is equal to P to N U times P to N negative U. So basically, you solve the recursive relation and get the explicit formula for the representation variety, and then you find out the relation between L and X and solve for X, and you plug X into the equation, the solution of X into the equation, and you get the A to P2 and G or U, something like this, and you plug into U back, and you have the A polynomial, but you have a radical, you want a polynomial, so you multiply Galois conjugates, and then you get the A polynomial here. So the proof is N, and this is the acknowledgement. And I prepare some words. Thank you. Is it too
Thank you for your
short?
talk. Do you have any questions?
Can you say a little bit louder?
Any questions, please? Do you have any questions? Then may I ask you a question? What is the percent of such knot not about or not in the table of knots?
Sorry, could you tell me
how
again?
many knot of this type is in the table of knots?
How many?
C to 4. C2 and 4.
Okay,
yes, this type of knot. How many is it?
Infinitely many. So this one, this one, if you have here four, this 4 is 4 in the second place, and then if you plug 1, then you have C24. If you plug 2, you have C44. If you plug
Yes.
3, C64, something like this.
If you instead 4, we change 4 to any number, how many such nodes?
Sorry, could you?
Is it typical node or exclusive node? Among
Are you saying that is it difficult to compute?
and another question: is it your method possible to other type of nodes?
Вот этот мужик, Александр
Could someone tell me again?
Is it possible to apply your methods to another types of nodes?
So I said that we did for C2 and 2. Matthew did first, and then we repeated, but with a slightly different representation. We did C2 and 2, and then we did C2 and 3, and this is C2 and 4, and we can do this up to C2 and 5 with this method, because up to radical we can cope Galois conjugates, but then C2 and 6 already it is difficult. But then by the other method, it's not the explicit one, but somehow the way to compute it is by densifying. That's what Jessica Purcell and Thompson, Matthew, and then Hugh, but they are doing that. So it's not the explicit one, but anyway, they are now making the formula to compute a polynomial. And then Patterson also made some formulas to compute a polynomial for double twist knots, and some double twist link by Tran. But they are so far they are small amount of a polynomials still.
Okay. Thank you.
Thank you.